Guys, so as I said, you have to look at the PowerPoints and study guides posted in iCollege. And there are 7 items in there.
Sorry, but we cannot see the screen.
The screen? Okay, hold on. You get the share, Firefox, share. Can you see now the screen? Can you see the screen? Yes? See the screen?
Yes.
Yes, no? Unmute yourself. Whenever you want to talk, unmute yourself.
Yes.
Yes, you can see the screen. So as I mentioned before, that we need to study really those 7 PowerPoints, which I'm sorry, and do the whole thing. One minute. So those are 7. If you study them, I think you will have a big success. Those are covering most of the units. So from our data, from our experiences through the years, they have problems in 2 topics. They score very well in all the topics of Chem 12, 11 content, general chemistry, part 1 content, except when it comes to stoichiometry and structure, visible Lewis dot structure and the shape, electronic shape, and the molecular molecules. That's where the problems are. So we'll review today is possible. Then I'll make up. I'll send an email saying in the weekend maybe we can go over. So today is stoichiometry the whole time because that's the topic which is really very difficult for students. And then we can make for the final review for the whisper and the electronic and the molecular shapes of the molecule. And the Lewis dot structure, of course, because the whisper, the shape of the molecule depends on the Lewis dot structure. So let me now unshare here and then go and share the PowerPoint. And the PowerPoints are here. As you can see, about I'll stop sharing. PowerPoints here. So we have different PowerPoints. So we can take, this is the stoichiometry. Those are 7 big topics in the PowerPoints. You can see, you can study the molarity solutions, and there are about significant figures. Then all the topics are there in those 7 PowerPoint slides. So on those slides, they can run to 40 slides. I mean, 20 questions with their answers about each slide is question and then their answer. So let's look at the, let me take one here out of the way. You can see that this is a question here, and you can expect something like this in the final exam, but different type of settings. The question will be rephrased, and maybe the molecules are different, but it's the same concept. So an initial reaction mixture of oxygen and fluorine is shown to the right. That's not to the right, but to the bottom. That's oxygen plus 2, which is, let me use the, so you can see that's the reaction here. And I can ask fabric here, has nothing to do with the stoichiometry, but this is a type of the reaction. What type of reaction is this? Oxygen plus 2 fluorine give you OF2, oxygen difluoride. What type of reaction is this? Somebody will tell me. What type of reaction? Unmute yourself and you can answer. What type of this reaction? Come on, guys, don't let me down. Please. Oh, everybody is listening? Hello? Hello? Listening, or what type of reaction is this? Stop.
Synthesis?
Synthesis? Yeah, the synthesis, or what the other name is. Synthesis, yes, correct. What's the other name is? The answer is correct, but what's the other name? It's a
Combination.
Combination, yes, that's a combination. It's called a combination. Now you have a combination reaction between oxygen and fluorine to get to oxygen difluoride. So now, which of those pictures here, that's what we are looking at. That's our key here. The black ones is fluorine, and the white circles here, oxygen. So fluorine molecules and oxygen fluorine and oxygen molecules, they come together, mix together, and then produce OF2, oxygen difluoride. Now, you have to look at the ratio. 1 mole is understood, not to 10. This is 1. So the ratio is 1 to 2. What? To 2. Correct, guys, to 2. Sorry, that's 2. So 1 to 2 to 2. So which one represent this? The picture here. Correct ratio. 1 to 2 to 2. Tell me. Somebody will tell me. Look at those pictures and tell me which one. Somebody? Hello? Just look at A, B, C, D. What's the correct answer? Somebody? Hello? Everybody is with me, or everybody is not with me? Somebody can look at those. Which one? Hello? Are you with me here? Yes, no? Somebody is with me? No? Okay, so, well, which of these is the correct answer? This is fluorine. This is oxygen. When you mix them together, let them react together. So you get a molecule, which is half of it is white, half of it, and 2 of those are the darker one are fluorine. So you get something looking like this. 1, and then here 1, here's 1. And those are the darker one. Those are the darker one. So that should be supposed to be your molecule. This is your molecule. Here's the white circle. That's your oxygen. And this is the fluorine here. So guys, which will have a seconds here? Somebody will tell me? Okay, so no answer. So that's wrong. It's wrong. That's expecting one oxygen, two chlorine, correct? And the ratio is twice. The ratio is twice. So this is wrong. This is wrong. And this is the same thing wrong. Might be correct, correct? This might be correct. So, and this might be correct. Now, the answer is between B and D. And which is correct? Which is correct? Which is correct? Both of that, they give indication this to be a correct answer. Now, if you look at this, you have 1 mole of oxygen, moles of what? Oxygen difluoride. So here you have only oxygen fluoride, correct? So there's no ratio. It's not showing the ratio. This one here show you 2 molecules of oxygen. Will give you how many? 4. 4 of what? Of the oxygen difluoride. Everybody's following me? Everybody's following? So the ratio is 2 to 4 means 1 to 2. So the answer is this one here. Because it shows the ratio between the oxygen and fluorine. So it's shown to the right, which representation shows what would be present after the reaction is complete. Okay, so the reaction is oxygen, and here the oxygen is the fluorine is limiting because it's consumed. There's no fluorine molecule left. The only thing left is oxygen. That's you have to have a limiting kind of, because you have an arrow here. That's a limiting reactant calculation or more ratio. So you have one of them become complete, which is consumed. That's nothing will be left out of it. This one here will be in excess, and that's the answer is correct. Answer is B. Although correct, but D is not correct in the sense both of those are limiting. That's not true. One of them should stay in excess, and the other one will be consumed. So it's missing the excess, the excess molecule. So here, this one here does not show excess, which is here in this sense we have up to 2 to 4, which is 1 to 2. Okay, so now let's go look at the guys. Everybody's following? So everybody's following. What type of reaction we have here, guys? Don't let me down. What type of reaction we have here? What type of reaction we have here?
Combination.
Combination again. That's correct. Synthesis or combination. So you have 2 reaction combinations. Now you look, initial reaction mixture of nitrogen and hydrogen is shown to the right. Which presentation shows what would be present after the reaction is complete? Now always remember, this stoichiometric reaction, you have limiting reactant which will be consumed, disappearing, and you have one other reactant will stay in excess. Correct? One will be in excess, one will be limiting. So now I give you the hint. That's the key. Well, whites are hydrogen, the 2 dark ones nitrogen. When you mix them, one nitrogen is dark, and the three are the hydrogen, that's ammonia here. So which one of those is correct? Which one is all of those? That's the key here of those molecules. Each molecule by itself on you. Okay, so you have nitrogen and you have hydrogen. That's not before the reaction. This is pictures before the reaction. When you let them react, then they will give you ammonia, which is this one here. So which one of this is correct? Is this correct? They produce ammonia? The answer is again, this is correct, but does not have an excess. You have to have an excess reactant there. The limiting to correct has to be one of those is in excess. So whether it's hydrogen or nitrogen. So let's look at all those together. How about C? C? What C? C is not correct because you have a problem with this. You have a problem with this. What is this? This is NH, correct? Nitrogen is dark, and you have the hydrogen. So there is no molecule NH. So that will take the whole thing out to your consideration. Okay, so how about B? Well, B, you have both reactants are there. This is hydrogen, and those are nitrogen. That's not the case, as we say. If you have a chemical reaction, one of the molecules, one of the reactants will be disappearing, and one will stay in excess. So this one here, both of them are present, and the products are there too. But it's fooling us because both reactants are present. So this is hydrogen, and those are the nitrogen, and that's not true. One of them has to appear, so we have one limiting, consumed 100%, and one is still staying as excess. So which one? Let's look at this. This is 1, 2, 3, 4. 4 ammonia, correct? And we have, and even to look at the ratio is not there, correct? Have 5 of nitrogen and 3 of oxygen. How about here? You have 3 of or 4 of ammonia, correct? Circle those 4. And you have 4 of here of oxygen, of nitrogen. And then you have 2, which is this one here, and this one here, of hydrogen. So it means that's the relationship between the poles will be what? 3 to 2, correct? 3 to 2. So we have 1, 2, 3, 4 ammonia here. So this following, so this is yeah. 2 molecules of hydrogen, and we have how many nitrogens? Nitrogen is 1, 2, 3, 4 nitrogen. But is the ratio correct? Look at me if the ratio is correct. So if the ratio is correct, somebody will tell me if the ratio is correct. So we have 2 hydrogens and 4 ammonia, and 4 ammonia, and how about nitrogen? Nitrogen is not ammonia here. This is nitrogen. Guys, well, the ratio is not correct. The ratio is not correct. but at least they are really they really correct. So what's the difference between A and B? What's the difference between A and B? Somebody will tell me what's the difference of A and B? You'll tell me how we know which one is correct, A or B? How we know if they are correct, A or B? So then you go back to your original thing and then calculate or add those all the hydrogens 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and the nitrogen is 1, 2, 3, 4, 5, and 6. So four hydrogen plus four hydrogens plus how many oxygens you have, how many nitrogens you have? 1, 2, 3, 4, 5, 6. This is not for 1, 2, 3, 4, 5, 6, 7, 8. This is 8. 8 hydrogens and 1, 2, 3, 4, 5, 6, and 6. And they combine nitrogen and hydrogen. They combine themselves is what? 1 to 3. 1 to 3. 1 to 3. So now you can test A and B and see which one is correct. Which one is correct? So it turns out you will have hydrogen is connected 3 times with nitrogen. So if you look at this picture here, each one hydrogen atom will be connected to 3 of hydrogen. So the amount of hydrogen left will be smaller. So hydrogen in this case is limiting, and the amount of nitrogen will be in excess. So A is the correct answer. A is the correct answer. Here is telling you that almost they are identical. That's not true. You have 1. This is hydrogen. 2, 3, and 4. And you have the same thing. 4. That's 4 hydrogen and the molecules and 4 molecules of nitrogen. That's 1 to 1 ratio. That's not true. That's not true. So the only thing left is the last one is correct. So those are not correct because they are just, this is the product here. That's not true. You have to have limiting and excess. So it looks like from A, multiple choice A, the limiting is your hydrogen because that's our left. The excess still large amount is nitrogen. So we'll clear everything here and we'll go for real calculation. So let's see here. So from the beginning or from the middle inside, see how is the so the limiting reagent or a reactant for a given reactant can be recognized because it is the reagent that, and you look at all multiple choices and you tell me which one is correct. So I'll give you 1 minute or 2, so you tell me which one is correct. So which one is correct? So tell me which one is correct. Reagent for a given reactant can be recognized because it is the reagent that what, as I said, consumed what? Almost completely. And it's not in excess. After the reaction is done, it's almost done. It's already gone, almost. But the excess will be still there, present. an abundant amount. So which is the correct answer from this? Somebody will tell me.
D.
Be used up first. Yes, that's correct. Will be used up first, but has the smallest mass in the reaction mixture, is present in the smallest molar quantity, and has the smallest coefficient. No. So A and B is not has the smallest mass in the reaction. That's you have to prove it through the mole ratio. The moles, you have to calculate you have using molar mass, and you have to do actual, not the actual mass. We deal with the dealing with moles first. Is present in the smallest molar quantity. That's will be used up first. Well, that's will be used not up first. That's not correct either. So it will be consumed totally after the reaction is done, not first. At the end of the reaction, not at the beginning. So that's, you see, those type of question is very what they call very confusing. So if I would say the correct answer from this, if we revise, again, those are not ACS exam, those are looked up study guide from the ACS study guide, and then try to shape them or mimicking, copy them in the ways the rephrase one. But if I would say is this one rephrased, that would be correct. So that would be correct. Okay. Smallest number of moles. If that's rephrased, mass is you can give the grams, but the grams can tell you nothing. So anyway, so this one is not correct. This one is not correct because those are completely at the end of the reaction, not first, at the end of the reaction. Not first, at the end of reaction. Okay, so the only that the smallest coefficient, that's not correct either. So those type of questions, it's very somebody is telling me a new word I learned from the other class, but this is called in English. I didn't find it in German or French or Spanish. Bambuzi, very tricky, very vague. Somebody heard about the word bambuzi? No. That's a very tricky question. So the answer will be close to be if we really reshape it a little bit by number of moles. The number of moles that has the smallest mass. That's not true. That's not true. You might have both of them smallest mass, but their molar mass is huge, so the number of moles are. So that's, so let's see what they have their answer is. Let's see what their answer is. So let's all those here. But the answer here. Yeah, so the answer is D, but it's not correct. It has to be at the end of the reaction. You understand my point? Everyone is following? Answer is D. Their answer is D. But I will say it's the smallest number of moles during the reaction. It will be the smallest mole of the products of the product. So is limiting reactant definition is that is the limiting reactant is the reactant that consumed totally after the reaction is done. And it is recognized by the small amount of mass of the product. We are always calculating the product based on this limiting reactant. So I think that all the choices are not correct. It's not consumed first, but it's consumed when you check at the end of during the reaction. You cannot trace it. After the reaction is complete, then you can see it's disappearing. It's completely consumed. So, but anyway, so as I said, those are not ACS. Those are homemade ones based on the study guide. Based on the study guide, and therefore the students, they have not to buy the study guide. This is but the rephrasing and with watching for the copyright. So we saw it balance this reaction and tell me which one is correct. Balance. What type of reaction is this? Somebody will tell me. What type of reaction is this? What type of reaction is this?
Double displacement.
That's correct. And how is the ratio? Which one is correct? Coefficient ratio, the more ratio. What do we have to put? You have 4. And which one is correct? Elimination. Remember what to eliminate. First, to eliminate, there is no fractional ratio. A is eliminated at once. Correct? And the second one will be eliminated is larger. 4, 2, 2, 4. No. It has to be always more ratio. That's what nature is telling us. There is a chemical reaction, always the more ratio between reactants and products, the smallest as much as you can. It cannot be large. So 4 to 2 to 2 to 4 is very rare. You will see some reactions, they have larger ones, but it's very, very rare cases. But we always you see ratio among the reactants and the products is always smaller ratio. So it has to be between this, we call it elimination, multiple choices elimination. So A and B, so I eliminate A and B, save myself time. So I have to consider B and C, those two. So which one is correct? Which one's correct? Ready? Just put those numbers in, see. Which one? Just put H and C. If you think that C, just put here 2. See? 2. And see if that's correct. That's not correct because 3 multiplied by 2, for example, sodium here is 6. Sodium is 2. So C is not correct. The only left is B. So 1, okay, to 1 to 2. So now you can see if, how about the sodium? Sodium is 2 here, 2, and sodium is 2. So that sodium is correct. Iodine is iodine is 2. Iodine is 2. Silver is 2. Silver, yes. So the answer is what? B. The answer is B. Everybody agreed? Everybody agreed? So let's take this one out. So the answer is B. Always remember the technique of elimination of multiple choices. So always there, always will be with us. What type of reaction is this? What type of reaction is this reaction? Reaction. Somebody will tell me what type of reaction is this? Guys, tell me. So this here still? Hello? Answer me, please. Unmute yourself, please. Unmute yourself and talk to me.
Combustion.
That's a combustion. That's correct. That's combustion. That's a combustion one. So now which one is correct? Which one is correct? Now the combustion is the rare cases. The combustion can have what? Larger what? Ratios. That's the only reaction type that has larger ratios because of the fact we are looking at complete combustion. This is called a complete combustion. If I have beside those two, carbon dioxide and hydrogen, I have unburned carbon, which we call this one soot. Okay. Soot, SOOT, it's unburned. Extra carbon is not burned, it's not combusted. So this one will be partial what combustion, but we don't have it. We don't have a soot. So therefore, this is a complete combustion. In complete combustion, the ratio you see will come very large, will be very large in complete combustion because you are using a large amount of oxygen to ensure yourself that really all the carbon is combusted. Nothing will be there as a soot. So you have to use a large amount of oxygen so that the ratio will be very high. So which one of those is the correct answer? Which one of this will be the correct answer? Somebody will tell me. So in this, that's the only case. Combustion reaction is the only reactive type because the ratios are very high. All the other types are very simple. That's because you have to ensure they give you complete combustion, so you have to use a lot of oxygen there to ensure that there is no soot is forming. So, which of the multiple choices is correct? Which of the multiple choices is correct? Which one? Somebody will tell me. This piece of paper and run it through. So, but this one here is very hard to eliminate because that's the only thing. Combustion reaction is the only thing that has larger ratios. So you cannot say, oh, that's large. But if that's like single displacement, double displacement, combination, decomposition, those are small ratios. But when it comes to combustion reaction, then the ratios can be very, very high. And this is understood the fact that you need to have a complete combustion and you don't have soot, so the amount of oxygen will be large. So, which one is correct? Which one is correct? Somebody will tell me? Somebody? What's the multiple choices one? A, B, C, or D? Which one? Piece of paper, so go run those through. So you have two carbons here, correct, guys? Two carbons. So your intuition say, how about the two? To ensure this carbon is correct. You have 14, correct? You have 14 hydrogen, you have two. So how about these 7 here? Correct? That makes hydrogen and what? Hydrogen and carbon is balanced. However, you have here 2 and 2, how much is what? Is 4 oxygen, and here is 7, 7 and 4. So here the oxygen is 11, right? 2 and 2, 4, and here 7 plus 4 is 11. However, here you have 1, add anything, and here you have almost one, yeah, one. I mean, you have two here and two here. So how many here? You have how many here? You have four. Correct, guys? You have four options here. So you balance carbon hydrogen, but after now you have two of them here, you have four options. Guys, is this following? So how to solve this one here? You have four on the other side, yeah, and the other side is eight. And so how will you solve this one here? So tell me, well, how about to put the 7 here? So it's 2 and 2, 4. And here you have 2. Let me take and 2, 4. So how much I have to put here, guys? How much I have to put here to make this one close to the same 11, this one 4. So somebody will tell me. Somebody. Any question? Any? You know how to do it, guys? Hello. Hello. Anybody? Anybody, guys? Oh, guys, hello. Somebody told me that's carbon 7, so our mistake here. Somebody will tell me this is not 2. That's a 7, guys. So nobody's with me. This is I can't see very well. So yeah, that's I have a surgery. I should be next week. So anyway, so this is 7 and 7. That's so 14. 14 plus 7, that's 21. I apologize. My mistake. I can't see the 7 one time. Nobody's with me. Hello? Unmute yourself. Hello? So, are you with me? Everyone? I'll have to stop, see if somebody's still there or not. Let's stop sharing. So, guys, unmute yourself. You have to unmute yourself. So, here it is. Mute yourself, unmute yourself, unmute yourself. Whenever I'm asking, so you can't hear me. Whether they can't hear me?
Yes, Dr. Atea, sometimes your audio is low.
My audio is low. Well, I put it all the way to the top. Let me just maybe make the whole thing to the top. Here it is. Okay, so that's 100%. So let me go on and look at this and let me share. Okay, so let's share the PowerPoints now. Share. We shared the ones, hold on, the ones who went to the committee. RT. Version. We shared this one. So, which one is correct? I was saying, because I couldn't see everyone, so
B.
7. So this is 7. This is 7, then you have to put 7 here. Hydrogen is 14. This is another 7 here. Correct? The answer is what? So you can calculate. This is oxygen is. So we balance carbon and hydrogen. Now oxygen is 14 and 21. So, and this is will be 19 over 2. The oxygen. 19 over 2 plus 2. So the 2 cancels out. This is 19 over 2. 2, the oxygen cancels 2. 19 here. And plus 2 makes what? 21. Correct? Is this correct or not correct? So, you said B? B, so that's really B. So you have to get rid of the 2 here. Multiply the whole equation by 2. Then it will be 2 here. This one will be 2. This one will be 19. This one will be 2 multiplied by 7, 14. One will be 14. Everybody can hear me? Everybody can hear me or not?
Yes, we can hear you.
Okay, so this is a combustion reaction, and we can expect this one here as larger what? Larger ratio. So let's clear the whole thing here. Let's move. This is another one. What is the coefficient for sodium chloride? What's here? Which one will be here? Somebody will tell me which one? What coefficient? If you balance this equation here, what will be the coefficient? Well, let's balance it here together. So I have calcium here. Calcium is 1. Calcium is here 3. I've started with calcium, for example. So how about putting 3 here? Correct? So I did mine for calcium. However, chlorine is 6. Chlorine is this. Now we have to put 6 here. So 6. Right. 6 here. Okay, so now the phosphate as a whole group is 2 groups. I can make a virtual parentheses here and say this is 1, so I have to put nitrogen is 6, so I have to put 2 here. So then I have this understood nitrogen, so 2 phosphate. So that's, and this is 1 understood nitrogen. So the ratio here is 3 to 2, 1 to 6. So what is the coefficient of sodium chloride? Will be what? Will be 6. Correct? Everybody agrees? Everybody agrees? What type of reaction is this? What type of reaction is this? Somebody will tell me what type of reaction is this?
Double displacement.
Double displacement, that's correct. Double displacement. So let me clear the whole thing here and see their answer, what they have there as answer. So they have the answer is 6, correct. That's what we got, 6. Okay, so this is another way, but then we'll go out of this balancing. That's the last one. So which one? When the equation is balanced, the smallest set of 4 numbers, what is the coefficient of nitrogen? What's the coefficient of nitrogen? Let's balance it. We have nitrogen is 2, nitrogen is 2. I'll keep nitrogen, it looks like, but they have another 2. So we have 4 nitrogen. This is nitrogen here. And there's another nitrogen here. So we have 4. However, we have 2 here. So how about if I say put another 2 here to make 4? 4, 4. You have 4 hydrogens, correct? And here 2 hydrogens. So how about putting 2 here? So now let's check on the oxygen, the Prober's oxygen. Is the oxygen correct? The answer is not. The oxygen here, we put 2 here, correct? Or to balance the hydrogen. But then you have 2 oxygen here, and here you have 4. So what do you think happens here? So what will happen? So is this balanced? No, that's not balanced. Although the nitrogen look balanced, but the whole thing is not balanced. So how I can get around balancing this, the whole thing? Let me clear this one here. So now the problem with the oxygen. So you can balance the nitrogen, you can balance the hydrogen, then you're stuck with the with the oxygen. So which way I have to go? Well, it turns out if this is, since you have 4, then let's put this one here. 4, correct? I'll leave this one at the end. So let's put the 4 oxygen here and see what will happen. Correct? So 4. And then I have 8 hydrogen, 4 oxygen. So I did balance the oxygen 4, 4. But then I have 8. And here I have 2. So I have to have what? 2 here. Correct? 2 of what? Then I have 8 hydrogen. And I have 8 hydrogen. But then the nitrogen is 4 and 2 make what? Make what? 6. Nitrogen is 4 and 2, 6. And here, how much it will be? 3. Okay, guys, as I said, there are no rules for balancing chemical equations. Always trial and error until you get to the correct answer. Number of atoms in the left equal number of atoms at the right. Or number of the groups at the left side, the atom side equal number of groups at the right side. So now we have our answer is which one? Nitrogen. Which mole ratio will have what moles? Answer is C. The answer is 3, correct? Now, what type of reaction is this? What type of reaction is this? What type of reaction is this? So, what type of reaction is this? When you kick out an atom out of its molecule, what we call this one here? So, what type of reaction is this? Hello? Now let's make it easier for you. It is single displacement or double displacement. So look at this, single displacement or double displacement. Hello? The answers. Guys, are you listening to me? I want this session to be interactive, not just one way talking. What type of reaction is this? Single or double, and why?
Single.
Single, it's not double, correct? Because if it's double, then you have nitrogen has to be in both sides, in the reactant sides. So we have here nitrogen and nitrogen, correct? And you will have, if it's double, you will have nitrogen here and nitrogen here, but we don't have nitrogen here. It looks like one of the nitrogen is kicked orphan by itself here. Whenever you see an element is kicked out of its molecule and is sitting orphan by itself, that's a single displacement, not a double. And I can show you here zinc. That's what you did in the lab, similar to this copper sulfate. Now, what will happen here, when you get the copper is orphan here by itself, copper here by itself, an orphan element here by itself, and then we get the zinc is taking over the sulfate here, took over the sulfate. So this is orphan here, the same thing like this one here, orphan picked up by itself. So that's a single displacement. Double displacement, they will exchange their what? Their anion. They will change their partners, anion with first with the cation of the second one. So they will swap. But there is no swap. The nitrogen is kicked out orphan by itself. The same thing here is kicked out by itself orphan. Whenever an element or molecule, nitrogen comes in nature as diatomic. So nitrogen is orphan here by itself. It's kicked out of both the molecules here. You kick nitrogen is kicked out of them. So nitrogen is orphan. So this is a single displacement. So that's correct. So actually, okay. So that's a good one. So let's start. Let's start with this. So you have determined the number of moles of carbon dioxide formed, CO2 formed when 2.50 mole ethanol, C2H6OH O. So that's a molecular formula, by the way. The structural formula, the condensed one will be looking different a little bit, but anyway, so undergoes combustion in excess of oxygen. So if oxygen is in excess, so what's the number of moles of carbon dioxide? That's balancing chemical equation. What number of moles? You have 2.5 of ethanol. So this one here, let me just go and look at the pen here. This one in excess. So we are not considering it for reaction. The yield of both products based on the limiting. The limiting is ethanol, oxygen excess. So it's not part of our consideration for calculation of the yield of the product. So ethanol is 2.50 mole, correct? So let's put it here. 2.5 mole. Ethanol says put et here. Okay. Oh yeah. So over 1. I need to get the moles of ethanol out. I look at the equation. I have 1 mole of ethanol, 1 mole of it. Stand up to how many moles? So this is 1, and this one is 2. It is 2 more of CO2, right? So the answer is mole F with the mole F cancels out. So 2.5 multiplied by 2, how much is that? The answer is 5.0. So 2 multiplied by 2.5 is 5.0. And those are absolute value ratio. They're not part of sig figs consideration. Our answer has to have 2 sig figs. And this is 2 sig figs here. 5.0 mole CO2. Mole CO2. Correct? So the answer is, what's the answer here? Is what? Is the answer is, oh, I see, I'm wrong with the sig fig. Here is 3, by the way, guys. I put 2, it's 3 here. So the answer will have 3. I'm sorry. So this, it says 2.50, that's 3 sig figs. So the answer has to have 3 sig figs, and the answer is D. Okay, so let's take this one out. Let's do erase this one here out. So guys, stoichiometry is very, very important, and I will make an email about the whisper and the electronic and molecular shapes, which is include the Lewis dot structure and polarity of the molecule. So let's look at this one here. Okay, we'll do one of these in grams, and then we'll do different. So you have, what is the mass in grams of ammonia necessary to produce 0.340 mole of NO in presence of excessive oxygen? What is the mass of ammonia? So what type of reaction is this? What type of reaction is this? I know this is what type of reaction is this? If you look at this, what type of reaction will be? Somebody will tell me what type of reaction is this. Come on, guys, don't let me down. Somebody, what type of reaction is this? Somebody? Hello? Everybody's following? No? Well, it turns out to be anytime I use pure oxygen, the reaction will be what? Any matter. Let it react. Any type of matter you have. Okay, guys, any type of matter you have, and you let it be combusted by the oxygen. So if you use pure oxygen for any matter, whether ammonia, organic, inorganic, that's at the end is a combustion reaction. For combustion reaction. Not double displacement, not nothing. This is really pure a combustion reaction. It looks like a double displacement to some of you guys. Combustion reaction. But remember that all the rule is anytime any matter I let it react with oxygen, this is reaction of pure oxygen for combustion. So that's a combustion, although it looks like double displacement. Correct? It looks like a double displacement, but that's not really true. That's not a double displacement. Because your product is made of 2 oxygen. H2 has oxygen and the NO, nitrogen monoxide, has an oxygen. So but anytime you let it react, any matter react pure oxygen, that's a combustion. Anyway, so let's calculate that. You started with 0.4 NO, correct? That's you have produced. And we need to know how many grams we have to put in as a reactant, as a limiting reactant, to get this amount of number of moles of the product here. So now we have to reverse it. We start from the product side. So we say 0.340 mole of the product, which is NO, nitrogen monoxide, over 1. And then you have to put the mole ratio here, mole, because you want to cancel mole NO. And then you are using in question is your ammonia to mole of ammonia. What's the mole ratio? Well, it is 4 mole of NO. That's the 4 here. Will stand up to 4 mole of 4 ammonia, 4 more of this. Guys, 4 more of this to 4 ammonia, 4 to 4. Correct? So mole NO with the mole NO cancels out. 4 and 4. They cancel themselves out. Now I need the molar mass. You said how many ammonia? I need the molar mass of ammonia, which is this one here, gram per mole, correct? So the top is 17.03 grams of ammonia. Added by mole. Yeah. All of the ammonia with mole ammonia cancels out. So you take 17.03 multiplied by 0.340, and your answer has to be how many sig picks you have here. Start at 3, so your answer has to have 3 sig picks. Here is 4 sig picks, and here's 3. The least one is the so your answer has to be 3 sig picks. So the answer is 3 sig picks. 17 divided by 0.3540. How much is it? So let's see. Let's calculate this one here. We have 17.3. $17.03 multiplied by 0.340. The answer is 5.79. 5.79. So there is no 579. The only answer will be, there 5.79. The answer is here 5.79. The answer is this one. C. Are these following, guys? Are these following? Yes, no. Are these following here? Are these following? Okay, so that's the answer. So let's take clear here. See if we can find another type. Okay, let's do this stoichiometry with the Avogadro's. Looks like whenever I have number of molecules, the word molecules, atoms, ions, formula units, that means you have to introduce yourself with your calculation to the Avogadro's number calculation. So that will be Avogadro's. So now self-contained breathing apparatus uses potassium superoxide, KO2, converts carbon dioxide and tap or water to exhaled air into oxygen, according to this type of reaction, correct? So according to this type of reaction. So now it looks like, what type of reaction is this? Now that's the opposite. You are not reacting with you're not reacting with oxygen, pure oxygen. You are getting the oxygen out inside the reactor. So what type of reaction is this? So that's not combustion. That's not single displacement. But what type of this reaction here? So you are converting CO2 into into oxygen. So what type of reaction is now? We said it's not single, it's not combustion, and it's not combination. Combination means, combination is what? Combination is synthesis, which is you're combining two or more molecules together to produce one single molecule. But here you are producing two. So now left is decomposition or double displacement. So single is not, combination is not, combustion is not. So you are left with two. Decomposition reaction, okay, or you have double displacement. Is it double displacement or decomposition? What you can tell? Decomposition reaction, one single molecule, but not the three. So not the three. So one single molecule will be decomposed into two or more molecules or elements. So decomposition means you are getting more products, correct? And we said double displacement when they swap their partners, when one take the other take the other. Which one then? So which type of reaction is this? So we eliminated the combination that you are producing one single. You have more products produced, more than one. Single, we said that cannot be a single because you are combining three molecules to get two molecules. So, but if you look at the whole thing, looks like it's more or less like single because you are kicking oxygen orphan by itself. Same thing with the reaction we did before. But how about decomposition? Decomposition is not decomposition. You have single molecule is decomposed in several ones. But here you have three, correct? You have three. That's not a sense, not combination. Combustion, you are not reacting with pure oxygen. So the only left is what? Double displacement or single displacement. Which one? Come on, guys. Is it the double displacement? It's not decomposition. This is not decomposition. Is it double displacement or single displacement? What do you think? Double displacement or single displacement? Come on, guys. Sometimes it's very, very hard to mention, but if you look at the whole thing, it's a redox reaction because the oxygen being what? Oxygen being oxidized. Oxygen is zero. The oxidation state of oxygen, pure oxygen, O2 is zero. But inside the reactants, oxygen is -2. So it's a redox reaction. So I would lean towards is somebody will tell me.
Single?
Yes, that's a single. Yeah, I will lean towards single. Yeah, I will lean towards single. But it's a redox in the sense this is whenever you kick one molecule or element orphan by itself, most of the time you're thinking it's a single displacement. Correct? You are displacing oxygen out of this compound and it's kicked out as orphan by itself. And it is a redox reaction because oxygen being oxidized from -2 to 0. 0 is so now how we calculate this? Self-contained breathing apparatus converting superoxide, potassium superoxide, KO2 into and H2O into O2. So how many molecules of oxygen gas will be produced from 0.0468 grams of carbon dioxide exhale. So the idea is you start whatever is given to you and whatever is given to us. Let me just undo this and come here. So then you start whatever is given to you. It's given to me is the amount of carbon dioxide being what? This amount. So I will start with this amount, okay? So I will say point. How many sig figs? That's point here, by the way. 0.04 68. Oops, sorry, 68 amps. 68. I don't know. It's not typing very well. It is change the color here, or the color. But anyway, so 0. Eight gram of CO2. I need to get the mole, correct? So this is 1. And then I put the molar mass is given to me here. This is the molar mass. Molar mass is 44.1 gram of CO2 per mole of CO2. Here, put the gram out, cancels out. I have more CO2. I need to get what? I need to get how many molecules of oxygen can be produced. I need oxygen, correct? So, well, I say mole of CO2 from the equation now, mole of CO2 to mole of oxygen. What's the mole ratio is? Let's look it up. I have here 3 mole of oxygen, and I have for CO2 is 4, 3 to 4. So mole CO2, the mole CO2 cancels out. Now I have mole, then I will say here 1 mole of O2, 1 mole of oxygen is Avogadro's number, which is 6.022 power 1023. Correct? 1 mole molecules, correct? Molecules. So that's Avogadro's number. This is Avogadro's number, 6.022 10 power 23 molecules per 1 mole. So the mole cancels out. The mole cancels out. Now let me change the color here. You multiply this amount here, it's given to you at the beginning, which is here, 3 sig figs, divided by the 4 sig figs, 44.01. Then you can multiply the whole thing at the top divided by the bottom, whatever you like. So you can multiply all those together here. By this top and multiply by the Avogadro's number. That will be your number at the top. Correct will be here. Then you multiply 44.54. Here it is. That will be the bottom one, which comes here. Then divide both, it will give you a number of molecules. So if you have time, just you can punch this one through and then tell me what's the value will be. What's the value will be? Somebody has it? What's the value will be? Somebody has it? Yes, no, no, yes. So how much is it? I want you to tell me which one would be the correct answer. Which one would be?
A.
A, okay. A, you said A, so let's see, let me double check. So, said A, so let me figure out, let's see what's the answer. The answer is the question. The answer is A, correct. The answer is A. We'll do another half an hour, then I'll stop there, okay? So we'll do A, this is A. Okay, so the, this one here. This one is the same way, correct? But I need the theoretical yield. That's another topic. So let's calculate this one here. So calculate for me this. Give you 1 minute to see it. It'll be until 10 o'clock and then I will call it off for today, for tonight. So what is the theoretical yield of NO that can be reduced from reaction of 3.50? So let me get this one here. You have theoretical yield. What is the theoretical yield? The theoretical yield is the yield based on limiting reactant. So we have to determine what is the limiting reactant. So you have two reactants. You have ammonia 3.5 moles and the oxygen is 4.0 moles. Which one is limiting, oxygen or ammonia? Well, I have to get the yield of one of those products, correct? Let's take, for example, one of the products. So mole of NO, natrium monoxide, based on oxygen, We'll do just not the graphs, we'll do just the first and then here mole of the product NO based on ammonia, the other reactants, to know which one is limiting, based on ammonia. So if you look at this, I have 3.4 of oxygen in the top and 4.1. I have 4.01 more of oxygen over 1, and then you go to equation. So then your number of moles at the bottom, and the top is more of your product, we say NO, correct? So equation here, I have 5 more oxygen at the bottom, and my product is 4. So that will lead to let's calculate this one here. So 4 multiplied by 4, 16 divided by 5. I can go and look at my calculator here. Is it figure the whole thing is 4 divided by 4.41 equal to this divided by 5 equal to 3.208. So we need we started with 3 sig figs, so we will be the answer is 3.21. The answer is 3.21, correct? So let me just double check with you. 3.21, yes. So, so mole of my product is, so here it is. So mole of oxygen cancels out. Now, here with the ammonia, I have how many? 3.50, 3.50 mole of ammonia ammonia here. And I have how many moles of ammonia here? I have 4 of ammonia, 4 moles of ammonia, 4 moles of, this is 4 here, this is 4 mole of NO. Mole NO, ammonia with mole ammonia cancels out. 4 cancels out. I have 3.50 mole of what? Of NO. So this, which one is greater? 3.50 or 3.2? 3. So that will be our what? Excess. That will be what our excess. This is the smaller one. This one will be limited. Smaller one here. We could say is to be limited. So do we have 3.21? Yes. The answer is A. The answer is what? The answer is A. So we'll have another half an hour, we'll finish. Any question about this? Any question? We calculate the theoretical based on the limiting reactant. First, you calculate the product based on both reactants and then determine the least number of moles. That will be your limiting reactant. So this is excess, and this one here is limiting. So oxygen is limited. And then from there, you can see how many moles you are producing from this limiting reactant, correct? Which came up to be A. So any question you have? So let's do another one. See if we can. So this is another limiting reactant based on this reaction here, guys. The reaction itself here. So this is limiting reactant. So if you look at limiting reactant, so you will take what's the mass of this is the mass of the product when point is reacted with this. So you have the reactants given to you in their what? In their grams. This is gram of TlCO4 and grams of H2O. So the first step is to transfer first the grams of H2O to number of moles. Correct? Transfer this number of moles. And transfer this to number of moles. Correct? And then if you have those moles, then you have what to do. You have their molar mass is given to you, the molar mass of, you take the mass here of H2O You divide it by 18, the smaller mass to get the moles. And you have titanium 4 chloride. This one here, you have the grams divided by smaller masses here. So now I convert those to number of moles. Then I base my calculation the same thing we did. My product based on each mole of reactor by itself. And then the least number of moles will be my limiting. The large number of moles will be my excess. So from there, I can get what? The moles of my product. Okay, guys, I can get number of my product. And then if I want the grams of my product, I have to multiply it by its molar mass is this to get the gram of my product. That's my product. Guys, can you do it? Can you do it? No. So let's take, this is your product here, correct? This is your what? Titanium 2 oxide. So this is your product. I want to see what the number of moles I'm producing, correct? And then transfer with the help of the molar mass, the number of moles into grams, correct? So let's look at this. You start first with the first one. Let's take titanium 4 chloride, which is, it is this amount here, 0.476. Let me take this one out. So, look at titanium, 0.476, 0.476 grams of Ti and Cl4. Divided by smaller mass, Cl4 molar mass 100, so that's a gram, 189 point, this is 9 here, 0.7 grams of Ti or and the top of mole of Ti. So now the grams cancels out. We have to look at the next step is, you have to look at the next step here. The next step is to get mole of TiCl4 out. The mole of Ti. Okay, to mole of my product, to mole of the product is the oxide itself. TiO2. Okay, what's the mole ratio here? This is 1 mole. Ti, the product is 1 mole here, and the nitrogen, and the reactant Ti is 1 mole. Okay, guys, so mole of the mole cancels out. You just divide this amount here by this amount, the molar mass of the gram cancels out. So that will give you a number of what? Of mole of your product TiO2. Now you do the same thing for H2O. So you take the H2O grams, 0.0501 gram of H2O. You have to do it for both reactants to determine what is the limiting reactant. So the H2O is 18.02 molar mass. So I have 18 0.02 gram of H2O per mole H2O. Okay, guys, grams, put the grams cancels out. Now I got look into what? Into the equation. I have one more of my product, Pi O2. This is understood metric range 1. And the H2O is 2. The H2O is 2. So to 2 mole of TiO2. So mole of, no, that's correct. Mole of H2O here, the bottom is mole H2O. The mole of H2O. The mole H2O with the mole H2O passes out. So now you have to determine which will be your number of moles of the product based on which reactant. So you divide this amount here, okay, guys, by this amount. Okay, and this is 1:1. Here you divide this amount here by this amount here. Okay, and back to there is a 2 here. So which one will be the least, you think? Look at the numbers here. Which one? So you can calculate and tell me which one you have. What do you think? Which one you have? Somebody will tell me which one. Which one? What's the answer here? Somebody has the answer. So if you have to get the moles, then you just multiply the mole by 79. The limiting reactant. Decide first which one is the least number of moles of TiO2, the product. And then this product here, you have to, this product here again, this is the product here, maybe changing the color here. The product here, multiply this number for the least number by its molar mass to get the number of grams. So which one? Somebody has calculated? Would that calculated? So which one is limiting? Which one is? Yeah, if you have this number here and you divide it by a huge number, 189.7, that's almost 190. So this number will be very small. You divide the small tiny amount by a larger number, so the answer is small. Answer is small here. Okay, and the answer here is large because this is, you divide by a smaller one, this one will be large. So, but if you divide anything by a larger number, so the answer will be smaller. So this is the limiting reactant. The limiting reactant is this. And you base your calculation after then taking this amount divided by the molar mass of TiCl4, correct? And then you multiply it by this, whatever the answer is coming out, you multiply it by the molar mass of 79.88. This is the product molar mass to get number of grams. So if you don't have the answer, so I can calculate. This is the limiting, and this is the excess. So according to what I see here, it said answer is A. So you can verify if the answer is A. You can verify if the answer is A, and that's given to you Here, can you see it? If I take the whole thing out, let's clear the whole thing, then you can see. The answer is 8. The answer is what? The answer is 8. That makes sense because you divide larger by larger molar mass to get small amount. Then you multiply it by the molar mass, which is about 80 of the product. Correct. TiO2. So this is another tab. Let's see if we can see another tab of those we saw those. Yeah, I think. Yeah, let's do this tab and then we can pull it up for tonight. Okay, maybe, yeah. So this one or this one, which one's the combustion reaction? It's a complete combustion reaction. It's not partial. There is no unburned circuit. So, oops, give you the answer of that. But I want you to look into this combustion reaction and tell me the same thing we did. You have to convert the reactants, which is the reactants are here. The reactants are here too. You have this one here, this organic compound, with another reactant oxygen, correct? When is this are combined? What is the excess reagent and how many moles of the reagent remains? How many is remaining of this reagent? Which one is the excess and which one is remaining? Guys? Any question, guys? Any question? Any question? Any question, guys? Well, you have to transfer the grams, as we said before, the grams of each reactant into moles by dividing them by their molar mass. This organic has this acetic acid, and we are combusting acetic acid and CO2 and H2O, and we divide the oxygen amount here, the grams, by the molar mass of it is here. So now I get number of moles. Then I go and look at one of my products, correct? I can take any of my product. I will take CO2 and then see which one based on this number of moles of the product CO2 produced. I base those number of moles for each reactant by themselves, the same thing I did the previous example. And then from there, I determine the least amount, correct? The least amount is my limiting reactant. The other one will be excess. Now, how much is the limiting reactant is? How much is the limiting reactant is? So I know the excess amount there. I know how much is the number of moles I started with, correct? You want me to do that? So let me maybe do it with a piece of paper. This is a good one. So this is a good one. So let me see. So let me here. So guys, if I take snipping tool and then maybe I take snipping tool of the whole thing here. Take the whole snipping tool and take the whole thing here to the copy this. Microsoft. You will not be able to see Microsoft. So let me see. And then I have to stop sharing. Guys, can you see the Microsoft Word? No, I don't think so. So let me stop sharing and then start sharing. Microsoft Word. Share it. And I'm sharing this one here with you. So this is the whole thing here. So yeah, So first, anyway, can you see the whole thing? Okay, guys, so here it is. What you have to do here, first, I have to maybe type in. So first is number of moles of CO2. I will base the whole thing on my product CO2. Correct? So let's see. Then I will say, I hope I can write on this. So moles of CO2 based on acetic acid, whatever the C3H8O. That's the organic. So that will be so there will be you start whatever is given to you. You have 3.8 grams, 3.8.00 gram of this 3H8O, correct? Then you divide this one here by its molar mass. The molar mass is the molar mass of this 60.01. So divided by 60.1 gram per mole. Okay, so you get number of moles of this. So that's number of your what is organic compound. That's a combustion reaction. It's a complete combustion reaction. So it is. Okay, that's number of moles. Now, I need to multiply this number of moles to look at the equation. I have 6 moles of CO2, 6 from the equation, 6 moles of CO2 gas to how many moles of your organic is 2 moles, correct? To 2 moles of your CH8O, correct? Oh, so that will give you what? The moles of CO2, the moles of CO2, the moles of CH3O will cancel out, and the grams will cancel out. So these grams here, let me just divide grams here, I will highlight it. All here will be cancelled, extracting it through, will be cancelled with grams of moles of this one here. So we cancel with, because we divided the gram of it is, this is C3H8. So, and mole of so the grams with the grams is because you are dividing, you cancel with the grams out. Okay, that would be, those are I'm subtracting this grams of this organic compound. You get what? The mole in the top and more to this. And so, all of one here. So then what you get is number of mole of CO2 left. So the answer is the answer is 'Let's see, the unit mole of CO2. So let's calculate this. Let's take this strike line out here. So this divided by this. So let's go and look at the calculator. I have 3 divided by 60.01. So this one is this, correct? Multiplied by 6, because you have 6 moles of this. Multiplied by 6 equal divided by 2, because that's 2 of this divided by 2. And the answer is 1.4. Let's copy this one here. Then I'll look at the sig fix later on. So the sig fix is all of it is 3, because all the values are 2 sig fix. So we'll come back and do this sig fix is 3 again. So this is moles of CO2. Moles of CO2. The gas based on CH3 C3H8O. So we do the same thing here. We'll do the same thing, but this now the second reactant is O2. So the reaction here. So don't worry, the answer has to be adjusted the correct answer. So instead of based on this, I will see based on O2. So let's start with this. You have how many grams of O2 you have? You have 7.38, 7.38 grams of O2. Okay, so divided by the O2 is 32.2, that's the molar mass, 32.0. Per more O2 per more O2. So it's the first step here. Then you divide by, look at the ratio here. You have 6 moles of, so then I'll put this one here. Divide by 6 moles of H2O, and let's take this one here out. You have the oxygen is 9 moles. So you have 9 moles of what? Of O2. 6 to 9 O2. So sorry. Okay, so the mole O2 packet extract this, we go out with the mole of O2, the grams of O2, all right, the mole of grams of O2. Then you have to multiply. This one is dark. Multiply by, so we did divide by 32, correct, gram per mole. And then we have 6 mole of CO2 to 9 mole of, and this would be equal to, so we have to divide this one here. So that will be, let's calculate this one with the calculator. So, correct me if I have it correct. Yes, the calculator. So we have 7.38, 7.38 grams of O2 divided by its molar mass, that's 2.0. Right. That will give you number of moles of O2, which cancels out with the moles by 2. Multiplied by 6. Whatever the answer is here, you have to multiply it by 6. 10 moles of CO2 are divided by the 9. So this is, copy this. I have right out here. Right out. This is more. So this is mole of CO2. So now from this one here, looking at this, this is the least number of moles. So this is the least number of moles, 0.149 versus 0.153. So this one would be, let's put it bigger here. So this is, out of this, we can say that the limiting is from what is excess, what is limiting. The excess is, the limiting is, according to whatever we have, we calculate is the C3H0, because has how many? 0.14997 more, which been transferred into 366. That will be 1.49, and this is 0.150 more, correct, of CO2. So now we know that we can eliminate out of our choices here, we can eliminate now 2 options here. So the option is not what they are asking. They're asking about the excess. So this is limiting. So this is can be X, and this is X. This is a limiting. So the excess is, and we have to put this one here. So this one here will be so here it is. This is so red. The excess is, oops, this, the excess, actant. And the excess reactant, the oxygen. And you can see this is excess, correct, guys? So this is 1.50. We base our yield from the limiting reaction, right? So if I have this moles here of this, so I would say I have this moles of CO2, which being the limiting, based on the limiting reactant. So I will say now we have to calculate how much is excess is excess. So we'll say, okay, the excess will be then the excess will be based on this amount here we have CO2. I have, get it, that's the CO2 moles. Okay. I have from the equation here, this is over 1. That's what this, my yield will be based on. Then I say, okay, let's see how much is the oxygen is left over. So I will say, multiply the whole thing by, then you go to the chemical equation in the top. It says you have 9 mole of oxygen, 9 mole of O2 will stand up to how much? Will stand up to 6 mole of CO2. 6 mole, correct, of CO2. So how many moles now of oxygen when it's wrapped? So the mole of oxygen here, or mole of CO2 here, let's strike it out. The mole of CO2 will strike it out. Okay. So now we have 9 multiplied by this divided by 6. So let's do it here. The calculator is. So you can see how it's time consuming type of this calculation. So take this one here out, clear out of this 0.150 multiplied by 9 and divided by 6. And this is, how much is 0.022. 225, 36 mole of O2 is being what? Used. However, when we calculated for the reaction beforehand, the number of moles came out to be the number of moles you have. Look at this. Number of moles for oxygen is, however, the starting oxygen R will be, then you calculate here, you just holding here, copy, go to this. So, go to this. So on this, let's calculate this. How many gram moles that will be? Equal to, so 7.3, let's calculate here. Okay, everyone, 7.38 divided by 32. 0.23. So you started this, wasted mole of oxygen. That's what you started with, 3-6-6. Let's do 3-6-6. So leftover of oxygen, then leftover oxygen 0.222. That's what we have here. The when we calculate that, when we calculate that? Here it is. Use so this one. Yeah. Starting. So will be one here. Copy this. And minus or to be used. So the answer is 0.231 minus 0.225, correct? So let's see here. 0.2. So we need out 0.231 minus 0.225, correct? Over is 0.006. 0.00. Of course, you have to treat Also, this is over. Okay, guys. So let's go back and look at the answer here. So the we know that's the we did X this one here, but the oxygen came out to be the CO2 is 0.14, limiting the oxygen is the excess. So the oxygen is excess. They're asking about the excess. And where is the excess, guys? Somebody will tell me. Our answer is correct. Here it is. That's the excess. And the other one is limiting. So all those are, this is limiting here, guys. This is limiting the 0.06 mole of excess is left over. Okay? Let's speak about the excess. The excess is oxygen and the leftover is 0.06. So I'll stop here. If you have any question, just email me and I will email you during the weekend. Sunday night or something like this. The guys, or Monday night, because therefore we cannot meet. The last day of the class is will be Monday 28th. Okay, so I'll stop here so you can look into this again. So what we did, we transferred the number of moles based on this product CO2, and we calculate number of moles for each one of these reactants. We decided the limiting reactant is organic, the oxygen is excess, and we calculate how much excess came out to be 0.06 mole left over of oxygen. Okay, guys. So and I'll stop here. That's, I think, enough for tonight. So now, any question, guys? Unmute yourself if you have any question before we quit.
I have one question about the lab final exam grade.
Well, I'm working on it, so I'm working it. I was in the hospital. I have 2 appointments for my surgery, so I did not have the time. I came late, so I didn't have the time to. But I grade them. Everything is graded. The written was graded, but I will grade tonight the lab, the practical one. Yes. What's your question? The grade is not done yet. I'm done with the written. I will put the written first, the grade tonight. So by tonight, maybe 12 o'clock or something, or so, I should be done with both. I'll put the grade, but the final grade, it will not be there until you have 1 day for the practical. So I'll wait for you to submit any outstanding stuff. I'll grade everything by tomorrow morning. So if you have any outstanding stuff, you have to do it, because at 12 a.m. tomorrow, I will close all the drop boxes in the lab, or the assignment section will be disappearing, except your grade for the final practical and written. Okay, so any other
Okay.
questions?
Thank you so much. Have a nice day.
Okay, so everybody, I will call it off tonight. I've spent longer time than the actual class, so thank you very much. Okay, guys, thank you. Thank you. Goodbye. Bye-bye.